Okay, so it's my pleasure to welcome today Sean Nercessian. I hope I'm not too bad as from pronunciation. Sorry for this. Today for this talk in the frame of the deep learning course here at IMT Atlantique, and I'm very glad to welcome you, Sean. So you're a principal scientist at Izozope, and you'll give today a talk on deep learning at Izozope. I'm very eager to listen to you. And maybe as a background, you have a PhD, a master degree from Tufts University, and then I understand you moved to MIT for some time before joining Izozope and being the principal scientist. So please, the floor is yours. We'll listen to you. And for those online, do not hesitate to raise questions in the chat. I'll follow up this and let Sean know. In the room, do not hesitate to raise your hand and do the same. I let Sean. Please, Sean, the floor is yours.
Sure. Thank you very much. Thank you so much, Francois. Thank you, Ronan. Thank you, everyone who organized this particular talk. I'm very happy to be presenting to you all today. As Ronan mentioned, I'll be sharing some insights on applications of deep learning at Izozope and Soundwide, and I hope that a takeaway from this talk is just to see the richness there is in audio deep learning, and it's really a very ripe field, and it's also not something that just stays in the research lab. It can actually make an impact in products and affect the way that people work in the audio industry. So I'll start with some preliminaries, and then I'll kind of get into some deep learning features that have been productized in Izozope and Soundwide products. I'll also explain vaguely what is Soundwide and what is Izozope and what are the differences and similarities, and then also get into some new research avenues as well. So I think Ronan did a pretty good job summarizing who I am and what I'm all about. The one thing that I can say about myself is that I'm not coming to you only as a technologist, but also as a lover and player of music, and it's easiest to call me a jazz-trained musician, but my interests in music go far beyond jazz music, and I also try to inject that line of thinking into our audio innovations. So yeah, I was at Tufts University, which is a small school outside of Boston, where I've lived my whole life, and then I went to an MIT research lab, and I was working primarily in radar signal processing. I guess another thing about my background to say is that before joining Izozope, I was working largely in image processing, and then image processing got me into radar signal processing. But for some 15 years time, I was trying to get into the audio field, and it didn't quite happen until I joined Izozope in 2017. And since then, my research has been in speech enhancement and restoration, neural audio synthesis, particularly as it pertains to voice conversion and manipulation, what we call automatic mixing, and applications of a particular technology called differentiable DSP. So you see Izozope / Soundwide. What are we getting at here? Historically, myself and Caroline Lacoste, who is also on the call, we've historically been from Izozope, which was a company based in Boston. Of late, in the last year or two, we've kind of partnered or paired up with a number of different companies in the audio industry, and we've come together on this umbrella called Soundwide. So while I was hired by Izozope, at this point, the research team that I work on actually serves the greater company. So this talk is basically going to kind of slant towards the Izozope productizations and applications because it's what I'm most familiar with, touch on some of the native instruments stuff as well. And that's for basically two reasons. One of them is like the familiarity that I have with these applications and my ability to speak about them. And the other is that these particular product lines have deep learning very front and center and prevalent in their product line. So that's going to be the focus of this talk. On the Izozope side, I don't know how many of y'all are aware of Izozope and what it does. Here are a number of products that we can kind of consider our flagships, and I only really bring them here because these are the products that I've worked on. The version numbers kind of indicate the products that I've worked on. So, for example, Ozone is our music mastering suite. We have a tool called RX, which is an award-winning audio repair and restoration suite. We have some vocal-specific products like Vocal Synth that tries to drive synthesizers using your voice and filter them using your vocal signal. We have another one called Nectar, which is kind of like a vocal production suite. We have something called Neutron, which is kind of a channel script for audio mixing. And then most recently, we released something called Audio Lens, which is kind of like a reference capturing program that integrates with all these tools that you can capture system audio of a particular sound or tone and be able to say in one of our products, hey, I'd like my master to sound like this Rihanna song, or I'd like my master to have the flavor of this particular, Guns N' Roses track or something like that. And I have to say that Izotope has been making intelligent audio processors for a very long time, basically from their inception, which we're going on 20 plus years. We have been making intelligent audio processors much before the AI craze and the deep learning boom. And it started, in many form factors, but we have a very top-notch kind of award-winning spectral processing guru, as I call him, Alexei Lukin, that had actually built up from his prototypes the grounds of what made our tool called RX. And RX started with modules that kind of can do invasive spectral editing, and then also different modules that can detect a particular type of anomaly and then apply the right form of spectral correction to get rid of that anomaly. So I will show an example of this, and let's hope that this all works.
I'm a perfect choice to join.
So this is called deplosive, is a particular application where plosives are basically these p sounds that you make when you vocalize. And if you don't have a nice pop filter in front of your microphone, or even if you have a pop filter, these might kind of manifest themselves as these loud, low bass thumps. So let's hear a before and after of running our deplosive technology.
And that I'm a perfect choice to join the space program.
So you hear those puss and space program, and they end up being.
I explained that I'm a perfect choice to join the space program.
So with spectral editing tools, we can automatically make those problems go away. Here's another example of a tool called Spectral Repair.
For content.
This tool is actually kind of like leveraging almost like this flavor of how Photoshop, you kind of select some regions and then you apply specific processing on them. That was actually kind of like the fundamental basis of the RX tool, that you see this image of the spectrogram and you can isolate areas that you want to have removed or attenuated, but it needs to be in a very smooth and consistent and subtle way. So let's see how this sounds for this particular example.
Text, here's before.
So we heard that guitar squeak. I guess that's the context. We had this guitar squeak.
Feature in spectral repair. So for context, here's before. And here's after.
So pretty good job at that. And this has kind of gone on to be a kind of award-winning industry standard piece of technology. A few years back, we had won kind of the Academy Tech Award. And I was very fortunate to be in the crowd to accept an engineering Emmy Award that we received for RX-7. Now we're on RX-10. So that was like actually pre-pandemic. It was one of the last fun things we did before the pandemic happened, was accept that award. We also have other mechanisms for intelligent audio processors that don't use deep learning, that depending on your marketing department, maybe people even would stretch the word of calling them AI, but it's kind of a stretch of the word, but marketing departments might do whatever that they're going to do to sell products and the like. But a number of processors that sense audio and react to the incoming signal to actually drive the way that processing is done. So in Ozone, we have something called a maximizer. This is what is able to provide loudness to masters. And you might have heard this thing called the loudness wars, where people try to drive these maximizers or limiters very, very high, so that you can make the mastered music sound as loud as possible. And of course, when you do that, you're doing a trade-off between maintaining the dynamics or losing dynamics. But on the other side, from kind of like an audio fidelity side, is you're going to kind of quickly get into a regime that you might start to introduce different types of distortions and clippings. And this maximizer is able to kind of like listen to the audio content and, based on the audio signal, be able to understand places where it might get away with doing not doing gain reductions because you might not psychoacoustically hear it, or places where because there's transient information. We need to treat the signal one way versus in other areas where things are a little bit more steady state, we can treat the signal another way. And this has been the basis of what we call intelligent release control modes. And we have 4 or 5 different modes of these in iterations of the Ozone Maximizer over the year. And the result is an intelligent audio processor. It's not necessarily using deep learning, it's not using machine learning, but intelligence nonetheless that is able to provide a loud and clean and high fidelity master so that it can be shipped to streaming services, physical media, etc. We also are pretty in tune with psychoacoustic masking and auditory phenomena and try to inject that into our work as well. So the notion of auditory masking is that the perception of one sound can actually be affected by the presence of another one. So if you hear the 2 sounds in isolation, you hear them at a particular level, but when you actually hear 2 stimuli at the same time, it actually might make you hear one of the sounds sounding as quieter than versus when you were hearing it in isolation. So in early iterates, we were able to kind of quantify that masking phenomena in a meter. And this metering can provide insights of how to improve clarity in a mix when you consider that you have a kick drum and an electric bass, and they occupy similar regions of the spectrum. There are going to be these kind of frequency clashes, and how to be able to solve these masking issues. Well, the first step is to be able to meter those and to actually be able to see visually where they're happening, in addition to trusting our ears to help guide users to make the right type of corrective adjustments to their mix. Later products have actually gone on to extrapolate the metering to actually automatically set up DSP. So now we have different manifestations of this, both in kind of static and dynamic type of processing. We have things that kind of sense masking between tracks and is able to use that to basically automatically carve out spaces for one element versus the other in a mix to kind of clean up the mix and get rid of muddiness. So with those preliminaries in place, I can go about talking about the deep learning presence in our line of products. So how did this rise of deep learning happen? This is probably not news to anyone here because you're in a deep learning course, but we had kind of classical machine learning algorithms for some time. And then when data became ubiquitous for many applications, like the image community always seems to have like maybe a leg up on the audio community because they kind of got that like data boom happening much earlier. And what we found is that when we're kind of confronted with a plethora of data, all of a sudden these deep learning or neural net type of approaches that were kind of considered maybe even subpar to like the other classical machine learning standards at the time, all of a sudden start to significantly outperform those classical approaches. And then with that became the democratization of deep learning in the form of open source and GitHubs and easy to use deep learning libraries and the like that are able to leverage parallelization of GPUs to enhance training and inference times of very complicated models. And it's kind of funny to see, like, you work at a company and there are different ways that different companies work. And we were lucky on the Izotope research team that we saw the kind of opportunities in deep learning a little bit earlier than our competition. And actually our explorations of the deep learning started off as a research team initiative, and now they've become kind of like a core pillar of the company. So it's kind of an example of how the tech end can really drive the strategy of how a company works. Here I'm giving a notional diagram. It's not necessarily a timeline because things kind of happened, like a little bit in nonlinear fashions and kind of asynchronous to one to the other. But I still kind of view our progression of deep learning kind of from left to right from here, where we started with like basic audio classification and so-called music information retrieval type of tasks. Eventually, we kind of pushed a little bit into this restorative spectral processing direction. And by this, I'm basically going to say applications of blind source separation is basically what I mean here. We kind of pushed the envelope a little bit further on our restoration tools to kind of like think of new type of synthesis tools that can be used for restoration. And now we're kind of forging a little bit in this direction of neural audio synthesis. And then kind of in like a parallel track, kind of an extension of this audio classification or MIR is this idea of blind parameter estimation and its kind of usefulness for things like reference matching, etc. So we're going to start with the audio classification, and we're going to work our way around. And then after kind of like summarizing this on the isotope side, I'll touch on some applications on the native instrument side as well. So we started with like our first productization of deep learning came in around 2016, when we unleashed into the world an audio classifier that is able to analyze audio and be able to detect the instrument type. This seems like not a big deal maybe nowadays, but at the time it was kind of like it made a big splash and our particular way that we use it. And we can go into some of the architectural details that kind of go into this. Is basically we listen to audio, we operate on Mel spectrogram. We're using a pretty, at this point, shallow convolutional architecture that was taken from image processing. At the time, there was something called AlexNet that was pretty popular. And based on that, we were able to formulate an architecture for carrying out audio classification, where we have an audio snippet, you play a little dung, 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 and you see that it's measuring it as 78% confident that it's a guitar sound. And that particular feature was kind of enveloped in a product called Izotope Neutron. And one might ask, okay, so what do you actually do with this classification? And when we talk about audio classification for music production, we like to extract as much metadata as we can from your audio when we analyze it. And this can help inform what we call auto mixing or auto mastering assistive engines that we have in our products. So what do we mean by auto mixing or auto mastering? Basically, it means we can listen to your audio and we can set up the parameters of our DSP in a way that we feel as though is appropriate for the audio that we've listened to. And in a context like, say, Ozone 10, which is our latest release of our mastering plugin, Ozone, we basically have genre-specific targets that drive many of our processors. So we can just analyze your audio, and based on kind of different genre-specific stats that we've acquired, we can set the tone of your production in both static and dynamic flavors. We can set up the dynamics processing that your source material is going to undertake, as well as the stereo width processing that your master might undertake. And we leverage genre classification to kind of point to what particular targets we want to be driving to this end. And we can kind of show you an example of this in a mastering context.
Into the before and our process.
So one thing I am going to note is that usually when you listen to mastering results, you hear one thing as like your input was very low, and then we do this thing called maximization and limiting, and that makes things sound louder, and then you feel as though louder is better. In this particular example, it might be subtle to hear over Zoom, but we are also applying what we call gain match so that we don't get tricked by this phenomena. So what we're going to hear is the results of our tone matching and our width matching and our dynamics matching that our audio classification was able to drive, basically.
We can make sure we're hearing a gain-matched comparison by pressing here.
I now understand that you are in an auditorium and it's very hard to hear that type of difference, but the mix got a little bit more open and brighter, and there's like a little bit more presence that comes from the stereo width matching that happened. And then if you smack on also the actual maximization, you'll say, wow, it sounds big and full, because the maximization also brought it to a good place. So in RX, it is actually a relatively new feature, but we're talking about kind of like our oldest manifestation of like deep learning came in this form of audio classification. And in RX10, which is our latest release, we have this thing called text navigation. And we actually kind of combine audio classification with a few other interesting bells and whistles. So RX is often used for post-production, for dialogue editing, and one particular application that has been more emerging is for podcasting. And in podcasting, you are often confronted with a scenario where you kind of have like a single mic setup, or you might end up having just kind of like the mix down of all of the interviewers talking to each other in one space. So in the most recent edition of RX, we've kind of combined 3 different machine learning type of innovations into what we're kind of lumping as text navigation. So we have ASR, or automatic speech recognition, that can listen to the audio and generate a text transcript. And we can also use that text transcript to like we have kind of like a search bar where you can say like, give me the instances where the word door was said or the word watch was said. And we can highlight just those instances. So we can quickly jump to certain pieces of what could be an hour-long audio file pretty easily. Another thing that we can do is this thing called speaker diarization, which is this detection of individual speakers. So you see here, let me hold my tongue on that. I will show you kind of how this all manifests in the example below. But the idea is that, you might have an interviewing and there might be different speakers that are talking at different times. And to be able to identify when a particular speaker is talking, to like kind of detect the number of speakers that are on the track and which speaker is present, could be useful in the context of RX, because what you can do is you can apply selective processing. Like say that somebody has this like problem. We have a module called mouth declick. It's a very disgusting sound actually. And we have the ability to identify when these mouth clicks are happening. It's just kind of like smacking of the lips and stuff like that. And we can actually in RX just isolate just those sounds and you can hear how distracting it can be in interviewing. And maybe one person has a mouth click problem because of maybe because of the way that they speak, but also because of the recording device that they're using. Like if they have a kind of like a very close, like a headset type of microphone, that might manifest itself. So you can apply selective processing to one speaker, but not apply it to the other ones. And then lastly, we also do some filtering using audio classification, which says if we know we're kind of doing these dialogue tasks, we don't want to run our ASR over non-speech regions. So what we have below here is we have this interview. And what you should be able to see is that there's a text transcript of this interview. You should see that when I've injected this little like these little guitar notes, we know not to transcribe text over there. And we are also able to classify that there are 3 people speaking in this audio interview. And we see that we're kind of saying when speaker 1 is active, when speaker 2 is active, when speaker 3 is active. So this is kind of showing the visual, and we have some YouTube content on this as well.
The change in Gregor's voice could probably not be noticed outside of the wooden.
Yeah, so you can see the change outside of Gregor's door, et cetera, et cetera. There's some that is like pretty ubiquitous, like, on our cell phone devices and stuff like that, but we've kind of brought it to the RX app in our latest edition. And then speaker diarization. In this case, I think it might only be 2 speakers, but let's see. Yeah, so here's one person talking.
If it's too dark, it will limit your furniture strategy.
Right. I mean, I have a friend who bought.
So you see how it highlights the different speakers, and it's understanding when that change of speakers happens. So that's kind of like the speaker diarization component of that. So let us continue onwards to restorative spectral processing. And here, as I mentioned, this is basically application of blind source separation. And this might be a problem. I don't know if it was studied during the course that you were taking, but it's a pretty extensively studied problem in the field, and it has many different applications and many flavors. Here we're exemplifying kind of like the notional, very conventional training configuration, and actually kind of like how the model works when you model the source separation as kind of a spectral processor. The idea is that, like, say we want to create a noise suppressor for dialogue, that we might have a vocal clip, or we have an interview, but it was recorded out in the field, and there are all these car horns and different environmental sounds and stuff like that. And we want to create a machine learning algorithm that can isolate just the vocals and not have any of those noises in the final take, and it sounds like it's kind of like studio recorded dialogue. So what you do in a machine learning context is you might have a database of clean speech, and then you might have a database of these different environmental noises that you want to be able to suppress out. And during training, you make random mixtures of those. And because you have a ground truth of like the spectrum of your clean speech versus the spectrum of the noise, you can train a neural model that will be able to basically infer what the separated source spectrum might look like. And in this particular methodology, this is kind of exemplifying the very conventional so-called spectral masking phenomena, or kind of convention, where we model this with kind of like a I guess a multiplicative residual connection is really what to call it, where we say that the neural network is primarily actually inferring a mask that goes from 0 to 1, and that basically assumes that to provide source separation, what we're going to do is just attenuate certain time frequency bins to actually be able to get the clean source. And if anyone is in kind of like audio music production, what this is tantamount is to having an equalizer. And imagine that you have an equalizer that has a very, very fine-grained frequency control, and it can be automated very, very precisely and very, very quickly. This is effectively what we're doing when we're doing blind source separation using the kind of spectral masking convention. And we have many, many exemplifications of this. The first iterate was what we call dialogue isolate, which is kind of exactly what I described, of like being able to denoise speech and get rid of stationary and non-stationary forms of noise. When we released this, our users came back to us with feedback requesting that we specifically make a tailored solution to what we call the removal of lavalier mic rustle. So what a lavalier mic is one of those clip-on mics that you might put on your shirt, your blazer or something like that when you're having a meeting. And every time the mic ruffles up against the clothing, it makes this kind of rustle sound. And because we're so in tune with kind of like the post-production world, we had many post-production engineers that say, hey, we have the on-set sound that we had it with a lav mic, and there was wind and it created all this rustle noise. Can you give me a catered solution for just the rustle removal? Then we kind of extrapolated further on this concept to do speech dereverberation. The concept is pretty similar, except that now the source of interest is the kind of clean speech or the direct path, and the dirty or kind of like the noise is actually just the reverberant signal that you can create random impulse responses and convolve with your clean speech, and then treat that as kind of like the noise signal that you want to be able to filter out. And then lastly, we also have musical source separation, which is extrapolating this to more than just kind of like this two-class problem, and being able to take, say, like a full mix of music and be able to isolate the individual constituent parts, like just the vocals, just the bass, just the drums. I think that as a deep learning class, y'all probably know about this pretty well, because there are a number of services that do this now, but we were kind of pioneered as one of the first to do this in kind of like an app-facing way. So if we talk about dialogue isolate, here's an example.
There has been nothing has been changed. It's all the same. It's war, it's fighting, there is no security, no guarantee to go from one place to another. There has been nothing has been changed. It's all the same. It's war, it's fighting, there is no security.
You see it's much more cleaned up in this thing. And this is really like a one-button process, basically saying like run the net, and then we can kind of combine the noise and the signal components in whatever varying gains that you want. So we can also talk about music rebalance in this context, which is basically our musical source separation module. So here in this particular instance, imagine that we have a recording of the Mars Volta, and we want to extract out just the vocal part of this clip. And this is showing what the input spectrum looks like. And then you press a button, and then we kind of retain just the singing or kind of vocal component. So let's hear that in action.
Let's take a listen.
Way far down, I sink ever deeper now. Yes, I go low. 'Cause when you come around, I go way far down.
Just the musical parts, just the bass part, just the drum part, basically. So kind of let's push on this restorative processing a little bit further, kind of going a little bit away from just the restorative spectral processing and kind of thinking about maybe in more of like a synthesis context. This is a project that I personally worked on and developed. It's called spectral recovery. You might also hear this in the field as speech bandwidth extension. The idea is for some reason you have a low quality speech signal, like a Zoom recording, MP3 codec, telephony. These are all different channels that are going to degrade the speech, the audio quality of speech for whatever reasons, usually to limit the amount of bandwidth that's needed to do the transmission. So in this particular example, we have an audio sample where we see that the upper frequencies are non-existent. We see that there are these spectral holes that are kind of created by things like compression algorithms, like MP3 compression will create these spectral holes. And then lastly, in this particular case, we also have a low frequency roll-off. And you see this in telephony, especially, that like the speech doesn't even go all the way down to, DC or to something like 20 hertz, which is kind of like the lower end of the hearing. it might actually have like a roll off and not actually kick in until like 200 or 300 hertz. And so the audio sounds very tinny. But we have a processor that basically recreates all those frequencies that don't exist, fills in holes, etc. So let's hear what that sounds like.
My wife and I just bought a Spanish revival house. It's got high ceilings and exposed beams. My wife and I just bought a Spanish revival house. It's got high ceilings and exposed beams.
So this is really something that, like, we have some examples of this, that like telephone speech actually can start to sound like it was, podcast recording speech. So, things of like when you have someone interviewing in through either something like Zoom or Skype, or like straight up, telephone hotline, which I guess is not used as often these days. These are ways of like kind of like repairing and restoring the frequencies that actually didn't even exist in the transmitted audio, but existed in the original source. I also want to just kind of like, I know that y'all are much more into the tech of it, and just kind of like to like notionally talk of like a progression that we were seeing in the research today, that things started in kind of like on like the audio restoration side, things kind of started in this kind of like spectral RNN type of processing. And then a few years later, we saw the emergence of these kind of convolutional sequence models that are showed to be kind of like higher fidelity than some of like the earlier RNN-based types of approaches. And then, in the last few years, we've seen the emergence of stabilized generative adversarial training and time domain models. The research today is kind of pushing in this direction of something called diffusion models. And I don't know if y'all go over that in the classroom or not, but the basic idea of diffusion models is that instead of trying to solve one hard problem in one go, you try to solve like 100 small problems, and it kind of makes the training a little bit easier and more stable to do. And you see this actually, all the DALL-E 2 and all those crazy image stuff is kind of rooted in stable diffusion and the like. And now that's starting to see some, application in the audio space as well for restoration. So we kind of went over this top rung, and I could kind of talk a little bit about this little side quest here. I'll get into neural audio synthesis kind of at the end, I believe. Where we're going to talk about blind parameter estimation and how this is like another application of deep learning that we have at Izotope. So we have this product called Dialogue Match, and this is kind of like a very, it might sound like a very niche thing, but it's like a very important thing that recording engineers and post-production are dealing with. And this is the idea that they record sound for TV and movies, and there is the sound that they record on set, and then there's the sound that they might have to go back and re-record certain parts in the studio. And so the recording engineers or the mixing engineers are kind of like faced with this task of being able to say, like, how can we combine the live sound, which sometimes also has more energy and is actually kind of like the sound that they want to go for. But if we have these very sterilized takes in the studio that we need to inject certain clips, and this happens all the time, basically, how can we make these things that were in the sterile environment, how can we make it sound like it was like we can place it in a live environment? And we have some DSP solutions for doing some of these things, like to match the tone. We have a so-called equalizer matching algorithm that is a DSP solution. We also have different iterates of what we call ambience matching, which is basically trying to create noise floors or noise textures that kind of match what was going on in the live sound. But then what is also kind of like a very strong perceptual cue is kind of like the reverberant profile of like the recording space, and that's kind of a function of many things: the space that you're in, and then the kind of like relative geometry of the recording sources and the actual speakers themselves. And so we created this algorithm that can infer what are the right DSP parameters to set a reverb to, so that like something that was like processed by the real world might actually sound like passable when you kind of apply a sterile clip with a certain type of DSP settings. I think this will make sense when I show the examples. But what I want to show is just kind of like notionally how we had trained such a network, and this is leveraging some work from a few years past, where you can take unprocessed audio like a clean speech data set, and you can you could render a particular form of DSP, like a reverb algorithm with known settings, and you have the processed audio. Now you take the processed audio and you run that through a neural net. And the neural net is trained in a way that it tries to infer or kind of like back out what were the parameter settings that were used to cause that audio to happen. And then the hope is that if you train that in a way that it doesn't like overfit to that particular training setup that you have, that can generalize to real world examples where now I record something in this room and I can set this up so that if I say, hey, do a match of reverb, it can actually figure out what are the DSP settings that would have kind of caused that. So why don't we just see this in action? Because I think that the application will speak for itself.
This is a real B&H customer story about Fred
Our first
Smithy
ad.
turning lemons to lemonade. Fred,
We would simply cease to draw breath if
So this is kind of like the sterile sound, and then there's the live sound, and then you can hear what the matched sound sounds like.
we limped lame with conscience to our graves without pursuing on all accounts. We would simply cease to draw breath if we limped lame with conscience to our...
You hear that live sound that is in there, and oftentimes like the performance is nailed in this kind of like a loud, like in the live context, but then they have to go back and fix a word or something like that. And the question is, how can we match the sterile sound to match the kind of like production dialogue?
to our graves without pursuing on all accounts. We would simply cease to draw breath if we limped lame with conscience to our graves without pursuing on all accounts.
So you see here that it kind of got that flavor of that live room, both in its tone and its ambience, and then also in its kind of like reverb profile. So you see it's called ADR. It's called basically automatic dialogue dialogue replacement. And so this is basically our way of basically being able to match the profiles of tone and reverb and ambience to make that happen. So I think the last one, so the last thing, I'm actually going to leave this till the end because there's going to be a live demo involved, and in case I have some demo problems, I don't want to waste time on this. But we also have an experimental playground. We call it Izozope Labs, and this is where we offer our subscription customers with kind of like behind the scenes features that are kind of like experimental. And one prototype that exists out there is called Morph One. And this is basically our neural based renderer of monophonic sources so that I can like say sing into a mic and I'll render it like it's a saxophone, for example. So I'll give a live demo of that. And this is kind of like starting to talk about the neural audio synthesis thing. And actually, I'm even going to get to more of that stuff before I do this audio demo. So this audio synthesis theme is emerging as kind of like a research avenue for us at the company right now. I did want to touch on the native instrument side. So they also have their version of MIR, music information retrieval extraction, and audio classification. It's stuff that they've played with. Of late, they've kind of become a powerhouse in neural based virtual analog and effect modeling. This is what virtual analog basically means. You have analog gear and you want to emulate it using digital mechanisms. So how do you go about doing that? And they also had, and Native Instruments also had some research on their own flavors of neural audio synthesis. So if we kind of talk about the virtual analog effect modeling, Native Instruments has a product, we call it Guitar Rig. And within Guitar Rig, we've released what we call intelligent circuit modeling. And this is basically exactly as I said, we have the analog gear, we have the digital emulation. And there was a time when this was all done, using DSP, and it required a lot of domain expertise to get it going. And there were still problems with that it still can't be perfect, because even if you can match a schematic perfectly, the actual analog gear has component values that might have tolerances of 10 to 20% off from them. So then it kind of goes like a thing of I made it perfect based on the spec that I saw, or like my piece by simulation, and it's still not sounding like the analog gear. It's because there's a little bit more to it. And there are different ways of, being able to field that, but an emerging form of that is actually to represent the virtual analog models using neural networks. And there are also a number of papers. Throughout this, I've been kind of sprinkling different publications. We do publish in our research group, and I've been sprinkling a few relevant publications throughout these slides. So here are some examples of different amps that exist in Guitar Rig that are based on this intelligent circuit modeling. Kind of a bluesier sounding amp. So, the idea is that these types of guitar emulation software, you don't need to have walls and walls of heavy amplifiers anymore. You can have an audio plugin running in your DAW, and you have all these sounds at your disposal and you can even be able to tweak them in maybe ways that you can't tweak, the amps, or like be able to automate things and stuff like that. Anything that you can kind of do in a DAW. So here's kind of another one. I think this is kind of like a heavier rock type of amp, like more heavy rock and metal type of amp. So this is literally a neural net that is processing the audio samples that are coming into it. And then here's kind of a bass amp that was also modeled. So that is kind of, I believe, the extent of the productized manifestations that I'll be kind of going into. And then I'm going to talk about some new research avenues. One of them is kind of like my passion project. It's called singing voice conversion, or voice conversion in general, but particularly for applications of singing. So the idea is that I have my voice today, however I am. I feel like I have good musical ideas, but I personally think my voice is too thick and I don't like the sound of it on record. But if there are like certain target voices that might exist and a conversion model, then we can actually render my vocal performance kind of in effectively a different identity. And I have a number of different papers on that work, and the most recent one right now exists on Archive. And if any of you all are going to be attending the Izmir conference that is taking place next week, I'll be giving kind of a late-breaking demo on this work as well, and shopping it to different peer-reviewed venues as we speak as well. So this last manifestation of this work is using something called what I call different concepts that are based in this idea of a differentiable world vocoder or differentiable world synthesizer. And effectively, if we're going to kind of get into what voice conversion is doing, is many algorithms kind of follow this encoder decoder type of architecture, where the encoder needs to be able to separate out in a style transfer context. They call it like content and style. Basically, in the context of voice conversion, we call it like the identity information, and then the other aspects of the performance, like its pitch, its loudness, the linguistic content that you're saying at any given moment in time. So an encoder needs to be able to separate out that identity component and only be able to extract in those kind of other performance factors, because then what the decoder is going to do is it's going to have speaker information, and it's going to pair it with the speaker independent representation, and it's going to ultimately be able to infer acoustic features as the acoustic features that one might imagine would have manifested themselves if a particular identity had done the performance themselves. And then there's going to be some sort of vocoding methodology, perhaps, to be able to get the rendered audio waveform. In this paper, we also have an example where we don't need to synthesize a new waveform. We actually manipulate the existing incoming signal, and we have some tricks that it's really, it is a great marriage of DSP informed processing, making the ability to model certain neural tasks just that much easier. So we can give a result here. We have this demo page. This is on Archive, and it has a link to this demo page that say this is me. Out of nowhere, you came. Say here's a target singer.
As I sit and watch and wait for what I...
And the render.
Out of nowhere, it came to me.
So what does that mean? What's the implications of this in a music production context? Maybe it's already quite evident, but say that we have some song that sounds like this. I've been seeking something new. Whatever we can say about the music, the voice is not what I want for this production, but now it can be. Imagine that's all coming from just, all we're doing is we're giving an input source singing, and we're saying, we're pressing the button and say transform, And this is what is happening when we do that. Relevant to kind of more the native instrument brand, is this idea of being able to generate, drum samples. So like they have all these samples and these instrument libraries. And so in one of their recent works, they explore percussive sound synthesis using generative adversarial training. And in particular, what they're also interested is to be able to make the generative adversarial training kind of like controllable. Like they're kind of saying like, can we extract out some semantic factors so that we can actually have parameters that drive how the synthesis happens. So here are some examples of this work. This is very much like, picking random numbers, or like, if in the United States, we have these claw machines that they take your money and you try to get a particular teddy bear out of the machine and it usually doesn't work. But imagine that you just have this claw machine and you pick here and you say, give me this drum sample. Okay, this claw machine goes over here. Now give me another drum sample. What it's just doing is it's polling the learned distribution of the data, and is because the generative model has been able to generalize the concept notionally how drums sound and what the latent space of drums, like how it can kind of be like set up to be kind of like maximally efficient. We can be able to pull new examples from sampling the latent space. So these are just, as I said, these were randomly selected, not cherry picked examples. Oops. Furthermore, they provide this like latent space interface, and I think below, I think they're showing some of the ways that you can vary one of the parameters and see how it manifests itself in the audio. So they were able to see this particular dimension, and let's see if we can kind of back out what this dimension is doing to the sound. So we're seeing pretty obviously that we have kick drums, but then like this particular latent dimension is pretty aligned to kind of like a pitch kind of dimension. Well, I guess I'll have to see exactly all the difference if I can back out what they say, but I guess they've enumerating it as hardness, depth, brightness, roughness is kind of like the semantic qualities that they've associated to some of these axes that they've been able to kind of infer through the generative adversarial network. So some parting words to y'all. Actually, well, let me see if I can do this one live audio demo of the Morph1 technology. Let's see if this works. So, hello. There's some latency over Zoom that's making it a little bit difficult, but you can see that the flavor of this, you could sing into it and have it render as a particular type of instrument. Like here, I've selected the saxophone model and stuff. So this is something that we kind of ship to our subscription customers as kind of like an experimental perk that they get privy to because they're part of our subscription service. So some parting words for the classroom is to really note that audio and music technology is a vast and multifaceted field. Like it's not just, there are cool things that are happening in this field. It's not all just in the image processing and computer vision community. It has been a little bit slower on the uptake, but it's really hitting its stride. And like, it's like this, like, what a time to be alive type of moments to be working in audio machine learning. And as you can see, like really seeing how this unleashes and unblocks all sorts of new processing that we never thought could be possible, and that one could never do with like a standard DSP type of codification. Like we really need deep learning and data-driven models to make this happen. But in light of the ML craze, I don't know what is the curriculum being offered at the Institute. Please pursue both DSP and machine learning. Machine learning should be considered a tool in your arsenal of tricks. And I'm telling you, you can use DSP smarts to cut down machine learning model sizes, implications around latency, these sorts of things. And they can really very much work together. And even you can model the problem as like a neural solution in some way and use DSP smarts there. And I will tell you that Izozope will not just ship the machine learning as it is. We will always find some ways of being able to get added performance because we've brought some traditional DSP into the mix for pre-processing or post-processing, or just kind of like, you know, our interpretation of the signal model, etc. And I believe strongly that having both of those in your toolkit will expand your purview, and it'll help separate you from the pack, because there are many people that also pursue machine learning blindly, maybe not having as rigorous, say, like a numerical linear algebra background, or not understanding filter design as well as it could, but they can do crazy things using machine learning. And what I'm saying is that if you also understand DSP deeply, it will start to inform the way that you actually think about machine learning. So that is kind of like my adult or fatherly advice to the group at large here. And also my email, Ronan can pass it on to anyone. I'm shahan@izotope.com for now, and you can feel free to connect to me via LinkedIn. Thank you for your attention, and I hope that this is a time that we have ample time for questions.
Thanks a lot, Sean. I think that we can. Really great talk. I was about to ask you about what about DSP. Still already the answer. I think what is a really great message for students here. So probably time for question and discussion. So I would like to start here or online. I have a question. Yeah, maybe if you could move closer to the mic here for time to listen. C'est la bonne room.
Can you hear me?
Yes, very well.
I have 2 questions, 4 questions. Will you send us your presentation just to have a look at it? Will we have access to that?
Yeah, sure. There's no problem.
Okay. Thank you. And second question, the project you talked about where you have like a source singer and you change his voice to a target singer.
Yes.
Do you have any idea on when this might be working, like definitely?
No comments.
Okay. Well, thank you.
Cheers. Thank you.
Just the video of the talk will be posted online. So I will resend the link after the conference. Any other comments or question? Okay, I may have one. So
yes.
my background, Sean, is also in deep learning, but for research, for application to climate science, ocean science. And we also use the term differentiable physics. And so I was curious, I saw in the title of a different publication, you also refer to differentiable kind of scheme. And physics is because you want to implement like physical models, but still to get the differentiability. So I was curious to understand why do you refer in your case to differentiable schemes and what's
yes. Yeah, for sure. And I might start to speak about things that are a little bit outside my domain, but I could imagine the differentiable physics stuff you're saying is like, there's also a big push about actually trying to like model sorry, it's going to be the same word. I mean, more like when I'm saying differentiable, like I mean like ODEs. There's the whole idea of like modeling like ODEs with the neural net, that being something that's like differentiable, and that is one thing. Here, what I'm kind of saying about like differentiable DSP was this notion that actually kind of came out from a seminal paper a few years ago that basically said like we can enable more like end-to-end processing, end-to-end meaning that working like starting in audio domain and ending in audio domain, as opposed to like starting in a feature representation and ending in some feature representation that might not be 100% matched to the perceptual domain that we actually be running the tool in. Basically, the notion is because we have so many differentiable operations at our disposal now, we can actually start to implement certain forms of DSP using differentiable operations, and we can use that to drive what we call end-to-end processing. So in that application, they were like they were considering like a differentiable version of a harmonics plus noise synthesizer. And so the model in this case was trying to if say given just few cues about the speech, the performance like loudness and pitch, can we map those to synthesizer parameters that drive some sort of synthesizer? And so if you set up the machine learning problem to just infer the synthesizer parameters, that's gonna be okay, but you're only getting so far. What you actually care about is how it's going to affect the actual audio at the end of the day. So if you could codify the synthesizer inside the neural network itself as a trainable layer, then you can actually see the audio to the end. And that concept has been extrapolated in many sorts of ways. We have papers about it, about how it can inform equalizer matching. The singing voice conversion work that I have kind of pushes hard on this theme as well. And it can also be used for effect modeling. It's basically saying like, please just don't use the black box layers that are offered in the deep learning toolkits. See if you can make some custom layers that are based on either DSP thinking or DSP, the actual DSP processors themselves. Sometimes you can find vectorized approximations for these different modules, and you can have them live inside the neural model so that your cost function is the most effective cost function for the task at hand.
Okay, thanks a lot. Any questions? Yeah. So we have another question here.
Of course.
It's a simple question, but what language do you use for programming the neural network? And
yeah, so obviously this is like an interesting thing that like, I said that I was going to get into challenges and I didn't quite get there. I could say the challenges associated with productization. First of all of the actual model training and development is done in Python. Early on, I was an adopter of TensorFlow. I have kind of converted to the dark side of like, once you go PyTorch, I feel as though you don't go back a little bit, but I still feel like I'm pretty bilingual in this thing. And I understand there are certain reasons why I might gravitate towards one over the other. There's also the interesting question of like, how do we actually integrate these models into, programs? We code in C++, our production code that is like, the actual applications are in C++. And basically, I can say that we leverage the TF Lite API. For now, it's our running thinking of how we actually integrate machine learning models into C++. And that might change, and the means by which we actually convert models to that format might change in time too. And our evolution of this is like, these things weren't that mature. Like in 2016, when we rolled out instrument classification, there wasn't any C++ API. There wasn't any like easy mobile form factor thing to like be able to deploy your models on edge devices. So the first thing that we had done was actually, here's a conv layer, and we were actually using Theano in that stuff. I don't know if that you even know what that is, but it was like at some point in time we thought that was like the most performant machine learning language. But then the second that they dropped support of it, we were kind of like left stuck. But we were coding things in Theano, and then we had the model weights. And we actually were like, okay, we're going to implement the convolutional layer in C++, and we're going to make unit tests to see that it matches exactly the definition in Theano, and the same for recurrent layers, and the same for a dense layer, etc. And it quickly became tedious and not scalable, especially as machine learning became kind of a core pillar for the company. So we've been trying to find all sorts of different ways to alleviate some of the pains. I would still say that the pains, I still feel the pain. It's still there, but it's funny to see that on the research side, we think about like frameworks and new differentiable operations and new layer types and stuff like that. But the developer side of things, like there's an audio developer conference that just happened a little bit ago. They're all talking about how to make this port of the trained models in Python. How quickly can we make it into an audio plugin? That is just the answer. Can we do one button? Does it need to be two button? Is there some still work associated? If it's a one button solution, how performant is it? Does it still pay to do the bespoke solution, the custom made solution, because we get more performance out of it? These are stuff that I, on the research team, interface a lot with the development team and the integration team to try to solve these things. And to be honest, crudely, it's still a huge pain in the butt, basically, but we're working on it.
Okay, thank you.
Thanks a lot. Nicolas?
Hi, yeah, I had a quick question. You talked a little bit about diffusion models, like as being immensely successful as they are in image, especially in the text to image generation model. So what is your current stance on how this might or might not change neural audio synthesis and deep learning on audio?
Yeah, so my take on it right now, I want to show y'all a little bit. This is not so much from like a product perspective, but from just like where the research is going. We're seeing that diffusion-based models are coming into the fold. And what they boast is higher fidelity. The question that needs to be understood is like, you know, as I mentioned, the way that it does what it does is instead of solving one problem, they might solve 100 small problems. So in a generative context, this kind of means that like if a generative adversarial network was originally thought of as something that you take in a noisy latent vector and you immediately come out with the audio example, or you immediately come out with the drum sample, or immediately come out with the image. We don't do that anymore. We think about modeling it with this diffusive process where every single layer is just trying to be a little bit less noisy until we get to this final thing that is the, you know, the output of the system. But that means that you're running the network n times now to solve the n sub problems. So I know that there's some work in terms of like distilling that down, that you even train a diffusive process with n steps, but then you say, okay, can I learn a student model that is able to distill some of those steps into like half of the steps, or a quarter of the steps, or an eighth of the steps? And basically my feeling on it right now is one thing that is holding us back in audio is a little bit of this expectation thing that people in the audio field, they expect real-time performance. They put on a distortion plugin. You can play the guitar and hear it at the same time. You can put a chorus effect. You can put all these different effects, pitch correction, all this stuff. They've gotten used to this thing of like being able to throw all these plugins onto their products and not having that big latency associated with it and stuff like that. And then on the other hand, you're talking about these big diffusion models that need to run inference 100 times to get an audio example out. And this is a huge disconnect. So what my thought is that the research in terms of fidelity is saying this, but in terms of practicality, until we could find that like the solve the scalability problem, it might be a while. I think that the day will come that someday you will see some of those things, but right now I kind of question exactly how quickly that will happen.
Thanks.